Welcome everyone. I'm Alok Ranjan, Engineering Manager for Storage Platform at Dropbox. Today, we will discuss how we scale observability with Grafana Loki. Our agenda covers the context of our observability challenges, the technical and operational requirements we faced, our evaluation of different logging solutions, and finally, why we chose Loki. Before we dive in, let me give you some context about my background. I'm currently an engineering manager for the storage platform team at Dropbox. Prior to this, I worked at Big Switch Networks, VMware, and Cisco, primarily focusing on storage systems and scalable infrastructure. My team at Dropbox is responsible for ensuring our storage systems can handle massive scale while maintaining security and performance. To appreciate why this problem was so challenging, let's first look at the scale at which we operate. Dropbox serves over 700 million users globally, with more than 18 million paying users. We are handling over 1 trillion pieces of content, and we are processing over billions of new files uploads every single day. Let's start by defining what we mean by unstructured logs so we can better understand our problem statement. Unstructured logs are essentially raw data outputs that don't adhere to any defined schema, unlike the structured logs, right? Hive records or traces, which are neatly formatted. At Dropbox, these logs come from various sources, including our first-party code and third-party debug files, such as those found in warlog Dropbox. Because these logs lack a predefined structure, they offer a high degree of flexibility and detail, making them incredibly useful for real-time troubleshooting. However, that same flexibility means that analyzing them can be challenging, time-consuming, especially when you need to quickly pinpoint an issue during an incident. Let's go over our problem statement. As I said, unstructured logs are stored in var logs. Prior to our implementation or our adoption of Loki, we didn't have an actual logging solution at Dropbox. Developers used to SSH into individual boxes. We had a host rotation policy of 7 days. That means after 7 days, the host will be rotated out. So all the logs on that host will be deleted. Around that same time, we were also migrating from standalone hosts to containers. Because containers are even more efficient. They can just vanish any moment. Also, SSHing into a container to exactly go to warlog Dropbox was also not that easy. That was also a little cumbersome. So this was the entire problem statement. So from there, we gathered a high-level requirement. We needed to provide a user-friendly and secure interface that makes it easy for production service owners to look at their unstructured logs. As I said, our current process involved manually SSHing into hosts to retrieve logs, which was not efficient and error-prone. We wanted to automate and simplify this process. We wanted to make sure the system is capable of ingesting the entire stream of production logs without any modification to our application code. Finally, the architecture should be designed to seamlessly integrate logs from our acquisitions and other corporate assets. Yeah, from there, we gathered some more requirements on the reliability and security side. We wanted to provide at least 1 week log storage. And as you can see, since there was 7-day host rotation policy, this requirement came directly from there. We analyzed our metrics and figured out we were ingesting approximately 150 terabyte per day of logs. Today, it is way more than that, but that's where we started. We wanted to make sure the latency for P99 ingestion is less than 30 seconds. And for queries, it should be less than 10 seconds. We wanted to make sure our availability goal is 99%. We wanted to make sure we have MTLS enabled right from the day itself so that we are ensured that every connection is authenticated, secured. We wanted to implement strict access control based on service ownership. By segmenting access, we could provide better auditing. We can ensure only authorized teams can view and manage their logs. To further secure our logs, we wanted to make sure we are encrypting all the stored data using some sort of key management practice. And we wanted to provide a way to, or a mechanism for detecting, filtering, and redacting PII information if it ever leaked. We also wanted to make sure we call out some non-goals. We did not want to mandate any changes to our existing log format. We wanted our system designed in such a way that it can work with any unstructured logs we already have so that teams don't have to migrate to it. Our goal wasn't to replace any of the structured logging tracing or any of the metric systems. We only wanted this system to be used as a complementary tool, which focuses on troubleshooting rather than serving as any other solution. We wanted to make sure that the solution was not going to be a replacement for any of the analytics system. And lastly, we didn't want to impose any new logging practice on teams. We wanted to avoid mandating anything like how logs are produced or what the format would be, so that existing team owners don't have to feel any burden when this new system is added. Next, let's take a look at the evaluation metric. These metrics provided us with a framework for comparing different approaches. Cost was definitely the highest priority. We wanted to make sure that the total cost of ownership, including both OPEX and CAPEX, along with any potential contract risk, are accounted for. Performance was another critical metric. We wanted to make sure the logging solution could handle our ingestion rate and matches the query latency we had in mind. We definitely wanted a rich query engine. And since our engineers were very familiar with Grafana, we were highly interested in a solution which could integrate with Grafana. And along with that, we wanted to make sure there is ease of integration with our current observability tools. With the solution, we wanted the solution to seamlessly work across our existing infrastructure without major changes. And finally, security. We wanted to make sure there is robust data protection so that we can minimize risk of sensitive data exposure. All right, and now let's consider the do-nothing scenario. The pros, of course, were no additional investment. Cons was you would have to continue with manual, non-scalable, inefficient troubleshooting. So ultimately, the status quo was not meeting the modern observability needs. So that's why we didn't proceed. Now let's examine our evaluation of all the other logging service options. In this slide, we'll compare several potential solutions side by side. So the first one was externally managed SaaS. Here we'll use a logging solution offered by a third-party service. Of course, the pros were it reduces in-house management overhead, but the cons was a very high cost of operating it. And also, since we would be sending entirety of our logs to a third-party service, there was a potential risk of exposing PII to them. So that's why the solution was rejected, both because of cost and security concern. The second option was managed cloud logging, where things like managed search and logging solution will be hosted on a cloud framework. Pros was these kind of technologies have matured enough, they are scalable. But again, even for this option at our scale, the operational cost was going to be very high. And we looked at few solutions and we felt X was still not where we wanted it to be. The third option was self-hosted enterprise, where we will host some enterprise-grade log management system on our premises. Pros were you get all the rich feature set, you get very robust vendor support. But the cons was the licensing was still going to be very expensive and it would still need to run on our infrastructure. So that cost is there, plus overhead of maintaining it. So that's why we rejected this as well. The last option was building our own logging solution, just build a custom developed solution which fits our need. Obviously, this was the most exciting option, but this is not our core competency. And we realized that the observability field, like the vendor over there are so mature that it is better to go with some established solution than reinventing the wheel. Now let's focus on Grafana Loki. Being open source, Loki offers a low total cost of ownership compared to other proprietary solutions. which made it an attractive option from a budget perspective. It's optimized for Dropbox scale log ingestion and query, which means it can handle our massive volumes of logs we generate without compromising on speed. Loki provides a native unified observability interface through Grafana, and that was one of the major factors. Loki's architecture is pretty distributed, so it is designed to grow alongside your needs, ensuring that as data volumes increase, our observability capability would also remain robust. So overall, Grafana Loki ticked all the boxes by combining performance, cost efficiency, ease of use, and scalability, making it an ideal choice for our logging needs. What is Loki? Loki is an open source project, meaning it's free to use, inspect, and contribute to. And this has led to a very strong community engagement and a rapid iteration, helping it to evolve into a production-grade solution, actually. It is built to scale out across multiple nodes, ensuring that it can handle increasing volumes of log data. Loki is designed with high availability in mind, so it remains resilient even if individual components fail. The system supports multi-tenancy. You can securely isolate log data for different teams or services. This was critical for our diverse production environment. Loki draws inspiration from Prometheus, and it leverages a similar approach to metrics collection and querying, which makes it familiar to many of our teams because our internal metric system is also quite similar to Prometheus. At its core, Loki is a log aggregation system that efficiently collects, indexes, and stores log data while minimizing resource overhead. Now that we have talked about why Loki exists and how it differs from traditional logging solutions, let's dive into how it works at a high level. The first thing you need to get logs into Loki is an agent. For that, we have Promtail. One important distinction to make here is that unlike Prometheus, Loki does not use a pull model. Instead of scraping logs, Loki pushes them. This is one area where Loki is different from Prometheus. So why not follow the same pull-based model as Prometheus? The answer is simple. Logs are fundamentally different from metrics. Logs are generated at very high volume and need to be streamed efficiently rather than pulled periodically. Before we dive into the technical details, let's start with the fundamental reason why Loki exists. Many existing logging solutions are difficult to operate and expensive to scale. Loki was built to solve these problems by being very simple to operate and very cost efficient. One of the key design decisions that sets Loki apart is that it does not perform full text indexing. Instead, it only indexes metadata about each line. So why does this matter? Because in most logging solutions, the biggest cost driver is maintaining a massive index for full text search. Indexing every single word from every log entry means you need gigabytes, sometimes terabytes of index storage, leading to a very high memory uses and expensive infrastructure. Loki takes a different approach. It focuses on efficient metadata indexing instead of full text indexing, making it much more lightweight and scalable. Now let's break down how logs are structured in Loki. Every log entry in Loki consists of three main components: timestamp, label, and content. A timestamp provides precise time information for when the log was generated, down to the nanoseconds. Labels are key value pairs that serve as the metadata index, helping Loki locate logs efficiently. Content is the actual log message itself, which is not indexed, but stored efficiently for retrieval. By keeping the index small and focusing only on labels, Loki allows for faster ingestion and querying with minimal infrastructure overhead. This architecture is what makes Loki highly scalable compared to traditional logging solutions. One of the core concepts in Loki is the log stream. A log stream is simply a collection of log entries that share the exact same label set. This means that the logs generated from the same application on the same server with the same metadata are grouped together. For example, let's look at these log entries. logs from dummy service running on example node 1 form one stream, and logs from dummy service running on example node 2 form a different stream. By structuring logs this way, we ensure that the log remains organized, queryable, and scalable without the overhead of full text indexing. Now, let's talk about how Loki stores logs efficiently. Logs in Loki are grouped into chunks based on their label set. Here is how this approach works. Each log stream is stored in separate chunks. These chunks are sorted in timestamp order. A chunk continues collecting logs until it reaches a target size or a time node marker. Once a chunk is full, it is compressed and then flushed to an object store like AWS S3, Google Cloud Storage, Azure Blobs, or even a local file system. This chunk-based approach ensures that logs are stored in the most cost-effective way possible. Instead of relying on expensive databases, Loki leverages scalable object storage to reduce cost and improve retrieval efficiency. So, how do we retrieve logs efficiently in Loki? When a query is executed, Loki first looks at the metadata index to determine which chunks contain the relevant logs. For example, if we query service equals dummy service and node ID equals example node 1, for logs between timestamp T5 and T7, Loki only fetches the chunks that fall within the time range. It does not need to scan through all the logs, just the ones that match the query criteria. This makes queries fast, efficient, and scalable, even when dealing with massive amount of log data. Now, what if we need to query logs across multiple streams? Let's say we want logs from both example node 1 and example node 2. In that case, Loki will use the index to determine which chunk match our query. Retrieve only the necessary chunk instead of scanning all the logs. Then it will combine the result and display them in tools like Grafana. This query efficiency ensures that even large-scale logging systems remain performant. In addition to Grafana, Loki provides command-line utility like log CLI, which allow developers to interact with logs from the terminal, and it can be integrated with other scripts and workflows. By leveraging stream-based querying and avoiding full-text indexing, Loki provides a scalable and cost-effective way to store logs. When working with Loki, label selection is critical. High cardinality labels like trace ID, user ID, or dynamic path values can explode the number of unique log streams, hurting performance and increasing cost. Instead, we should favor low cardinality labels like cluster, app, or file name to keep things efficient. For example, even combining just 3 labels like log level, status, and path with a few possible values, it can easily create 36 unique streams. In this case, 4 into 3. So it adds up pretty fast. Now, let's talk about how we deploy Loki at Dropbox. But first, let's take a look at a simplified diagram of Loki's architecture. At the top, we have the main components of the write and read paths in yellow. On the bottom, we have an object storage S3 for storing logs in green. And on the right side, we have some shared components like the memcache clusters in blue and cluster-wide services like compactor and etcd in orange. Starting with the right path, logs are written to the distributors, which hash the log stream labels. Then they look up the hash ring in etcd and route them to the ingesters that own their hash range. The ingesters buffer the log chunks in memory, then eventually flush the logs to the object storage. In the background, the compactor merges the log index files in object storage for faster queries. For the read path, the query frontend receives a query and splits it up into subqueries, which are processed by different queryers. The queryers fetch recent logs from the cache in the ingesters or it fetches the older logs from the object storage. For a sense of the scale of our Loki deployment, here are some top-level metrics. We are processing on the order of 10 gigabytes of logs per second, and we store these logs for 30 days, which takes up about 10 petabytes in object storage. Excuse me. We have around 1,000 tenants, and our users are making less than one query per second. So as you can see, the system is heavily skewed towards write over reads. With Dropbox being a storage company, one thing we did is use our internal object storage as a drop-in replacement for S3. This has led to cost savings, especially the data transfer costs. With these lower costs, now we are able to increase our log retention from 1 week to 4 weeks. One other big difference between S3 and our internal storage is some performance characteristics. We noticed that S3 would gradually scale out to handle large reads. And because most queries are scanning many logs, this would lead to timeouts. Whereas our internal systems, they have reserve capacity, and we also have emergency capacities, so we don't have the same issue. Another thing is because the index files are so large, we still have to write them to S3. Loki supports isolating the access and storage of logs by tenant. At Dropbox, a tenant is a service, which is a group of projects. Because the logs are stored by tenant, there are performance implications. For one service, we had to use project as the tenant instead of service, because that service just produces too much logs. Excuse me. Before Loki, engineers had to use production SSH access just to view logs, which were present on the service host. With Loki, we have redefined the model so that each service acts as its own tenant. This means we are aligning with our existing permission model. What worked for accessing a service is now used to secure log access. So we have extended this model by adding a group permission, enabling teams to grant access to their logs to other teams when needed. And naturally, some teams even have permission that allow them to access all logs. To pull it all together, we developed a custom query auth proxy. This proxy intercepts each query to ensure that the user has permissions, which avoids the complexity and cost that would come from using Grafana's native RBAC. An approach that would also require us a separate data source per tenant, and also would have needed us to upgrade to Grafana Enterprise. One thing that comes up a lot is teams trying to share logs with other teams. For example, if team A wants to share their logs with team B must request permission. But because the permission is owned by the logging team, only we can approve it. While there is an incident or a SEV going on, this delay can be costly. So our solution for that was Breakglass, which allows any user with a justified reason to temporarily gain access to any service logs. And we keep an audit trail and use safeguards on the amount of logs a user can access. We run Loki in 2 data centers in separate geographical regions, and so that in case one data center goes down, we still have availability. At Dropbox, we call this multi-homing. Both data centers use the same object storage, and to route logs and queries to the correct Loki cluster, we integrate our DNS servers with load balancers. And now I'm going to go over some of the scaling challenges we faced. By default, Loki ingesters store a write-ahead log on disk. That way, if the ingester crashes before flushing the logs, it can recover them. At Dropbox, we disabled the write-ahead log to prioritize availability over durability. Loki supports per tenant rate limits to avoid the noisy neighbor problem. So what we did is set conservative default rate limit, and teams are notified by an alert when their service goes over those limits. Loki supports overriding rate limits per tenant in a file, and we distribute those overrides to Loki in minutes using our distributed key value store, and we hot reload these override files in Loki component that use it. To scale read and write, Loki uses hash ring to shard logs. Each ingester owns a range in the hash ring and periodically registers its range and health status in the ring, which is stored in a distributed key value store. The distributor, which receives logs from applications, uses that ring to route logs to the correct ingesters, plus replicate the logs to other ingesters. Here is an example of that. When a log is ingested, the labels for the log plus the tenant, which is usually the service in Dropbox, is hashed, and then the distributor takes the hash and does the lookup in the ring. Originally, we used etcd as the backing store for the ring. etcd is a distributed, consistent key value store that's often used for coordination and configuration in distributed systems. It is notable for being the default for Kubernetes, and it is also now widely used at Dropbox. One issue we had with etcd was write contention. Each ingester would send a heartbeat every minute and update the ring. Also, when an ingester joins or leaves the ring, it updates the ring. etcd stores the whole ring as a binary blob in a single. And every time the ring is updated, the whole ring is replaced with a read plus a compare and swap operation. With a replication factor of 3 and 67 ingesters for each, we had 201 total ingesters. So as you can imagine, there was a lot of write activity going on. Some ways the write contention would manifest is deployments would take hours because ingesters were pushed one at a time. And these pushes would often fail because an availability alert would fire. Also, because etcd is a single point of failure, we had some outages when etcd went down. Luckily, Grafana made memberlist the default distributed key value store for Loki and other projects, so we replaced etcd with it. Memberlist is a peer-to-peer gossip protocol, so we no longer had to maintain another component. With memberlist, the ring updates are propagated as smaller deltas instead of the whole ring. However, one downside is it is eventually consistent. So unlike etcd, which offers strong consistency. This means we still have to deploy the ingester slowly. But the pros are we no longer have to deal with write contention, a single point of failure, and honestly, we haven't had any issue in the last year using memberlist. We were also able to double the amount of ingesters after migrating to memberlist. Log indexes determine the query plan, including how many log chunks needs to be fetched and scanned. So they have a good deal of impact on performance. Grafana changed the index format from BoldDB to DSDB, which is based on Prometheus DSDB, so it just works better with a loglet. In summary, our goal was to scale and improve observability and Dropbox. We were facing challenges with manual SSH into hosts and digging through unstructured logs. It was a slow, error-prone, and hard-to-scale process. We evaluated several solutions and ultimately chose Grafana Loki for its performance, cost efficiency, and native multi-tenant support. As a result, we have significantly improved log retention, lowered cost, and enabled fast, secure access to logs across teams. So that's all for my presentation. Thank you.